Hello, students. Today we want to discuss some basic word problems. I know that you're aware of this, especially as you've been studying mathematics. Mathematics is filled with word problems, starting in general mathematics and moving on through algebra, geometry, where certain situations are described, and then you have to provide the mathematical symbols that are needed to solve the problem. And you will continue to do that as you do mathematics, of course, science courses, engineering, finance, all of those. Even in the calculus sequence, you continue to study word problems. And of course, in Calculus 1, one of the interesting topics has to do with optimization, where you use the derivative to maximize and minimize functions. So what we want to do today is just cover some basic types of problems that you can do at this point in your mathematical career. And you may have seen some of these before. And I just want to provide some techniques that I think will make the problems maybe a little bit more efficient and easier to solve, and problem techniques that you can share with others and hopefully improve your overall success with these types of problems. So let me share my screen. The first type of problem that I want to cover is the time, rate, distance. And what I want to do is show you how you can set up one of these problems and actually work to a solution that you can do confidently. So this type of problem, we don't deal with a variable motion. That's a calculus problem. So we have what we call the uniform motion, or distance equals rate times time. So students will say, how will I know what the problem is? Well, it'll be clear if you're given some rates, you're given some times, things like that will be very clear from the statement of the problem. So in this particular example, we have a boat, in Stillwater. A boat in Stillwater has a rate of 34 miles per hour. A trip upstream takes 21 minutes, and the return trip downstream takes 13 minutes. Now, what is the speed of the current? So you're thinking, well, that didn't give me much information, but it actually is more than enough. So when you think of a time, rate, distance problem, these are structured so you have two legs, so to speak, two parts of the problem that are in some way connected. So when you think of just the boat moving on the water with no current, you have a rate of 34 miles per hour. And so what's happening here, as you move upstream, the current is subtracting from your rate or working against you. And then when you return, the return trip, so to speak, just covering the distance that you just covered going upstream, the current will help you. That is, it will assist you. You'll move quicker. So what we want to do in this particular case, and of course I have R here for rate, it doesn't matter what letters you use. I'm just going to use X in this case because it'll be simpler and we're used to that. Now, when we go upstream, we will subtract X from 34 because the current will be working against us. And now you notice here, I've got this factor of 60 in the denominator. Well, when we have 21 minutes, we want to convert that to hours. So we simply divide the 21 by 60. So now we have the equivalent amount of hours. Now, our formula says distance equals rate times time. So we have, in this case, rate, which is 34 minus X, times the actual, rate, which is 34 minus X, and the actual time, which is 21 over 60. Now, again, this chart simply serves as a mechanism to organize your work. I think I found as I work with students, they tend to have better success when they look at the problem from a more strategic standpoint. That is, you set up the given information in an organized fashion, and then you can easily put the pieces together in a more competent way. So now, of course, downstream, the current is helping you out. That is, it's adding to the 34. So we have 34 plus x. And of course, again, we know it's better because it takes less time. So we have 30 divided by 60 to give us the equivalent time in hours. And then, of course, we go back up here and find the distance, which is the rate times the time. The rate 34 plus x times the time, 13 over 60. Now, at this point, just like I said before, the distance up equals the distance back. And so again, that is the piece of logic that ties these two parts together. So anytime you do a time, rate, distance problem, there will be some piece of the story that will allow you to connect the two pieces, always. So now we've got 21 over 60 times 34 minus x is equal to 13 over 60 times 34 plus x. Now, this is what I talked about when we had our first lecture, which is basically symbolic computation. That means that we let the symbols do the work for us. Notice from the very outset, even though we converted to hours, the form of the equation gets rid of those. So we can simply absorb the 60s, basically multiply by 60, they're gone. And now at this point, we just have 21 times 34, again, symbolically. We have 21 times the negative x, which we have here. And then, of course, on the right-hand side, we have 13 times 34, and we have 13 times x. Now, what we want to do is collect the like terms. And so that's fairly simple. Let's get all of our x's on one side. So we'll have 13x plus the 21x. And then, of course, we'll have 13 copies of 34 subtracted from what? 21 copies of 34. So no need to multiply that. We just want to think about factorization. So now, of course, we've got 34 common to both. So we just subtract 13 from 21, which is 8. So now, again, of course, here, 3 and 1 gives us a 4. 2 and the 1 gives us a 34. How fortuitous. So now, that's a good word. I remember in high school when Dr. Tremblay said that, I said, what does that word mean? He says, well, look it up. I said, okay, yeah. It's something that occurs that you don't really expect, but in many cases, it's a positive thing. It's like, wow, look what happened. That's really good. You know, like driving down the road and the traffic's not so bad. You're like, wow, that's a great feeling. How fortuitous, right? So now the 34s drop out and we just have x equals 8. So notice by setting up the problem with the correct parameters and then letting the symbols do the work makes this problem very efficient. Now, like I said before, when the numbers are really, really nice, it does make the problem a little bit less tedious, but you can always use symbolic logic and symbolic calculation to move to a simplified form. And then if it is required, you can always do an estimate. For instance, if you're in a physics class or a chemistry class and you've got some of the constants that are involved and you need a nice approximation for your clients, maybe your client is your professor who needs to see an approximation, then you can use the tools of a Google calculator or whatever. But this gives you a nice solution. And now, of course, we know the current speed is just 8 miles per hour. Now, let me just also say this. When you do the word problems, this is your validation. This is your proof. Albeit, I know you can work with numbers, fidget back and forth, and when the numbers are user-friendly, you could probably come up with an answer. But that is not what this is teaching you. Be sure that you work out the problem with the chart and the equations, and let the equation give you the actual response. This is very important because even though I don't think these problems are just the linchpin of our existence in college algebra, they certainly provide a good logical process that I want you to learn how to do. And again, your solution does not have to look just like this, but the components of your solution should be very similar so that I can read it and see that you understand it. Okay, let's try another one. Now, I have an example here that has to do with mixtures. Now, mixtures occur all the time. They occur in businesses. You may have a coffee business, a beverage business. You may have a restaurant business or something, or you go to your favorite restaurant and things are mixed all the time. The chefs, the cooks, whatever, are mixing things. Okay, so the idea is that something you eat, maybe it's something you are maintaining, like a vehicle, like in this particular problem. Mixtures are very important in the sciences and just in our daily lives. So in this particular example, and this is an interesting exam, which I feel like if you can master these steps, you can always set up a mixture problem. So here's what we're given. We're given 3.9 liter radiator. So you've got a radiator in your vehicle that has a volume of 3.9 liters, and it contains 75% antifreeze. Okay, so again, pretty concentrated. Now, a 50% antifreeze solution is desired. So what we're asked to do is determine the dilution required to produce this. And what I've written here is drain and add water. Okay, so maybe you're working with something and you're thinking, it's too concentrated, so you throw out a little and put in some water, but you don't really do it as a math problem. You just kind of intuit what you've got and say this will work. Again, not as precise, but the idea is apparent. So what you might be thinking is that, what is my unknown? Well, think about it this way. You drain part of the concentrated solution and replace with the same amount of the universal solvent or water. Okay, so when you make your assignment for the unknown volume, it can be either. You can say volume of 75% solution, or you can just say volume of water to be added, because they will be the same. So don't worry about how you define it. You can choose either in your definition. So just remember, when you work the word problem, you read and then you figure out what it is you need to know, and then that is stated as your unknown using whatever variable you like. So it's not required that you use particular variables or anything of that nature. Choose the variable that you like. Of course, here I've chosen X. Now, what I've done to make the arithmetic a little bit easier is to just go ahead and write the 3.9 as 3 9/10, and then just write that as 39/10 liters. Just write everything as fractions. I think you'll find with the mixture problems that if you write the percentages as fractions, you can get rid of the hundreds, get rid of the decimals altogether, and have a simpler equation. Again, this makes the process easy. Now, one thing that you have when you're mixing two items, we're thinking of percentage antifreeze. So we're actually mixing a solution of antifreeze with water to make it more dilute. But that actually puts a little kink in the problem, because, for instance, when we think about this, we're doing the draining part. So now we've got 39/10 minus X as the volume of the 75% solution. And then, of course, we're adding the volume of water. So what we're draining, we're adding. But notice, this has the antifreeze percentage of 75/100, or concentration of 75/100, but water has no antifreeze. So this term will have no impact, though it does exist, because it's important in the calculation process. It's important in the procedure to produce the more dilute solution. But now, of course, when you're done, you have 39/10 liters of 50% solution. So again, if you write the percentages as fractions, I think you'll find that to be very, very simple. You will have to get used to this, but I've taught many students these techniques, and now they know these problems, and they are able to help others through our tutoring center to be able to do these problems correctly. So notice here where I've got the labels, these are just that. They're not part of the calculation. So notice now, when you think about these particular types of problems, you're always going to have a concentration times the what? The volume. Concentration times the volume. Concentration times the volume. And the concentration can take on different parameters. Maybe it's cash per pound. Maybe it's percentage alcohol. It just depends on the type of problem. Now, the first thing we can do is see that the 100s absorb. So again, this is kind of the basic process. And now notice when the hundreds absorb, we're thinking, well, what can we do to get rid of the fractions here? We've got a 39 over 10 times 50, and then we have the 75 times 39 over 10 minus x. So at this point, if you like, you can just go ahead and multiply by 10. Well, when we multiply this factor by 10, of course, we're not multiplying both, so we move it into the factor where we need to fix it, so to speak. So we're left with 39 minus nx. Here's an example that's very important. Remember, when you multiply an expression by a number, you can use any factor to possess that new factor, that is, possess that multiplication. But there's only one. Do not make the mistake of saying, well, do I multiply it by both? No, because you're only multiplying by 10, not 100. So it's important when you do the symbolic calculation that you move the 10 where it's going to do the work that promoted its use in the first place. So of course, we need that factor here to absorb the 10. And then of course, here these go away and we're just left with 50 times 39. Now at this point, we're thinking symbolic calculation. Now, what you're noticing here is that I've got common factors here, but I noticed when I wrote this, I didn't absorb those 25s yet, but I did it on the next line. So notice here, we multiply 75 by 39, 75 by negative 10x, and then 50 by 39. Now, of course, probably more efficient to have done it up here, but now we can simply divide the equation by 25 to get rid of those factors of 25, which are just in the way. So 25 into the 75 gives us 3. Again, here we've got the minus 3. And of course, with the 50, we get a 2. Now, if we look at all of these, the process continues. If you look for common factors, then you make the numbers as small as possible. Notice we have a 3 here, a 3 here, and 39, of course, is 3 times 13. So now the 3's go away. We have 39, we have a negative 10x, and of course, the 3 here is absorbed, and we have 2 times 13. So now all of these numbers are relatively prime. We can't get rid of any other numbers. So if you like, we'll just go ahead and do this the old-fashioned. If you like, transpose the negative 10x to get 10x. And then, of course, now here, we're thinking, the easiest way to do this would just to subtract from 39 to 26. We could factor that, but that's easy just to do as it is. And of course, that's 13. So we have 10x equal to 13. If we divide by 10 the old-fashioned way, instead of using the zero product, we just get what? As an equivalent fraction, 1.3 liters. Now, here's another thing that's important. It is fine to write your answer this way, but if you're working a homework problem, it may ask that you write it as a decimal. Okay, that's fine. The problem will request an approximation if those are the formatting directions. But normally, you're fine with writing anything that's equivalent. It just depends on the way the problem is phrased. So if you have something that's equivalent to this, which is this would certainly be fine. So again, 13 over 10 is directly equivalent to 1.3. So this is important. If you take the time to work through the numbers here, you get a very elegant solution and you get a very precise solution. This is what I'm talking about. The mixture problems are going to be good training for number theoretic manipulation and algebraic manipulation that you will continue to do in this class and in pre-calculus and definitely in the calculus, because this training will allow you to work through problems systematically using the symbolic logic that makes the problem easier. So now, of course, remove 1.3 liters of 75% solution and add 1.3 liters of the universal solvent or water. So you can think of taking your vehicle in to be serviced, and there is some type of direction from your vehicle manufacturer that is now requiring a more dilute antifreeze. And so the mechanics that work on your vehicle would have access to calculations like this, so they can make sure that you had the correct dilution. Now, of course, maybe you don't have to do this. Maybe the manufacturer has sent the proper dilution to your service center. And so all they do is say, well, we've got 50% solution here. We're just going to drain what you have, get rid of it, and replace it with new. You might think that might be easier. Probably is. But the idea here is that if we weren't going that route, and we're trying to quote unquote repair what we had without maybe just throwing out the antifreeze solution that we already have, we can do the calculation. So again, if your mechanics were working, they could simply, go to your radiator and remove this using a calibrated type device, so they would know how much was removed, and then replace with the equivalent amount of water. So again, mixture problems are all over. We use the term ubiquitous. We're always mixing things. If you're in the kitchen, if you're in the factory, if you're having your car serviced, it's a common thing that happens in society. So these problems are actually useful. Okay. Now, here's an example that has to do with fraction work. Now, I think these are interesting problems, and if I can recall, when I was a kid, my mom would always put, back when we read newspapers back in the dark ages, she would cut the problems out of the newspaper and stick them on the refrigerator, because she would know. She says, well, Professor Ollis wants to do, well, at the time she called me Ron. And she said, well, Ron would like to do these problems. And so I remember at the time that they were always time, rate, distance, mixture, and fraction of work. And of course, when I became a math professor, the first thing the students asked me is, can you come up with some ways that'll help us do these so that we feel confident? So this is what I've been doing today. I've been going through types of strategies that make the problem easier. Let's just go back and summarize. With the mixture problems, we want to label the concentrations and work from the blanks. With the time, rate, distance, we want to do pretty much the same thing, but a table that lists rate, time, and distance for each leg of the journey. Now, when it comes to fraction of work, we are discussing completing a job, okay? So we think of performing a particular job, one person or more than one person, 2 people, 3 people, whatever. So you've got more people contributing to completing the job, so the job should be done quicker. So when you think of uniform motion, the fraction of work is the same. Everybody's working at a particular rate to get the job done. So what we think of in this particular case is the term fraction of work. And I want to describe to you how we get that, because right now it just seems a little bit like, well, that's just a made up term. So here, using garden hoses, Bob and Jim can fill the pool in 18 hours. So you go to people's homes a lot of times and you see they're filling up the pool with a garden hose. They're just using the water, that they get from the public utilities to fill up the pool. I mean, it happens all the time. So you have a neighbor, Bob has a neighbor, Jim, and like they've got a pool. One of them has a pool, and so they've got both hoses flowing into the pool to fill it up. It takes 18 hours. Now, of course, volume of water may vary between, and pressure and all of that may vary. And so it is apparent here that one hose is more efficient. That is, the volume of water is possibly more efficient. I don't know. We're not debating that. We're looking at what the problem is actually telling us. It says Bob's hose takes 40% less time than Jim's hose. So for whatever reason, Bob's hose is more efficient when it comes to the filling process, and that could mean many different things. Okay, so the problem says determine the time for each person to fill the pool alone. So if they were just stuck with one hose, how much time would it take? Okay, so notice the first thing I've done is reiterate the fact that if they work together, the job takes 18 hours. And that's important because we're going to use that in the calculation. But now we think, okay, what do we know? What do we not know? Well, we can say Jim, we can say job in T hours. So T is the unknown. So what we can say is T will represent time for Jim. And we'll just say that with the hose filling. So time for Jim. So that's our unknown. And then we notice that Bob's hose takes 40% less time. So we basically subtract 40% T from T. It's more efficient. So 40, well, that we like this, just divide by 20 and you get 2/5. So we've got T minus 2/5 T. So that's 5 minus a 2. So we get 3/5 T. Okay, that's how much time it takes for Bob. Okay, because the filling process for the hose that he's using takes 40% less time. That's it. That's all it is. It's not tricky. It's just basic logic there. So how do we get the fraction of work? Well, you reciprocate. So this is, in this particular case, job in T hours. So we say 1/T, fraction of the job per hour. And here we've got 3T/5. So we have 5/3T, fraction of the job per hour. Okay, so that's where we get fraction of work. We think about, okay, so we've got two people working on the process. Maybe you're raking the yard, maybe you have 3 people. Okay, so you're thinking the more people, the quicker the job's going to be done. Now, this is where we set up the so-called schema. For instance, we went over what we did for the time, rate, distance, and the mixture problems. So what we see is we have contribution from 2 people. We have Jim, we have Bob. So we have the fraction of the job per unit time times 18 because they can get the job done in 18 hours. So basically what we're trying to figure out is, what fraction does each contribute? Okay, well, 1/T times 18. That's the fraction that Jim contributes. And then Bob, his is 5/3T times 18. Okay, so when we think of that, we add the 2 contributions and we get 100%. We get what? The whole job. So the key here is this reciprocation that's going on gives us the fraction of the job per unit time, and we multiply by the 18 hours that they actually work doing the job together. And then we have the fraction of the job for Jim, and we have the fraction of the job for Bob, all as functions of T, which is the unknown that we're looking for. So this will allow us to solve for T and know how long it takes for Jim's hose to fill the pool. And then by virtue of that fact, we can figure out how long it takes for Bob's hose to fill the pool. So what's nice about these equations, because you have the one here, it's simpler. So now first we have what, 18 over T, and then of course the 3 will absorb into the 18 to give us 6. 6 times 5 is 30. Okay, so we're like, great. Same denominator, 18 plus 30 is 48. So we have 48 over T equals 1. At this point, you can reciprocate or just cross multiply, and you see T is 48. So now we go right up to here and see that Jim requires 48 hours. And then we've got the expression for the time that is required by Bob, which will be less. Okay, 3/5 the time that it took Jim to do it. And so now what you can do is just divide the 5 into the 48, and that'll give you 9 with 3 left over, right? So that's, 9 times 5 is 45. So that gives us 9 3/5. So 3 times 9 is 27, and 3 times 3/5 is just 9/5. So we can write this as a fraction. So 5 over 5 adds 1 here, and we're left with 4/5. But 4/5 is just 0.8. So now we see in this particular case that the job for Jim requires 48 hours working alone, and the job for Bob requires 28.8 hours working alone. Again, remember, if you are writing an equivalent decimal to a fraction, it's not an approximation, it's equivalent. And I know it's like you just keep saying the same thing over and over, but just remember, students sometimes think, well, the decimal is an approximation. No, the problem will always ask you if an approximation is needed or that it has been requested. Otherwise, when you give the exact expression, then you're fine. So again, remember, with the fraction of work, maybe most problems have 2 entities contributing to the job. You think a fraction of work, you think job is being executed. Simpler problems have less stuff in the story, okay? And the more stuff you have, the more logic you have to do. So I think this is a good example because it utilizes basic constructs to create a fraction of work problem. So just remember, the whole job is 100%. We want to know what fraction each of the entities contributes. And once we have that, we can actually have an equation in terms of the time where we've described that up here. Now, usually what it means is that there will be 2 people working, and I guess for problem's sake, they usually take different amounts of time, okay? And that different amount of time is what you have to be able to communicate through the mathematics, and that will vary from problem to problem. So don't worry about trying, again, to second guess the problem. Just read what the problem says and work it out, okay? So of course, you could change this problem by changing that percentage there. You could change this problem by changing that number, okay? So you have the ability to make up your own problems. I know at this point, you just probably want to work the problems that have been given to you, but you can also experiment with the numbers and see how that will change the outcome of the problem. So that's a really, really nice example that has to do with fraction of work. Remember, all of these problems have a set scheme, okay? And try to set up that scheme working from the entities that are providing for the problem. And then once you have that clearly, you can reciprocate. T becomes 1 over T. 3/5 T becomes 5 over 3T. And that's where you get the fraction of the job per unit time. Multiply by time, you get the fraction contributed. So that is why we say fraction of work. Now, I say that, maybe not everybody does, but it's certainly a way that describes what's going on here. Now, let's look at another example. This particular problem, I just want to go over another time, rate, distance problem, because I think in general, students tend to have a little bit harder time with them, but I don't know, that could change. Sometimes students need more help with the mixture problems, but again, don't assume anything about the problem until you read it. But I have found that usually the fraction of work tend to be the problems that students do the best. Now I had this worked out, but I wanted to write down the problem on a separate sheet. This says a 750-mile trip is taken by bus and train. Again, these are idealized. You think if you're doing this, we don't live in a perfect world, but this is describing a voyage. And so if we kind of stick to, the basics of this, we do get a solution that has some realistic value. So part by bus, part by train. The bus has a rate of 40 miles per hour. Well, that's a scenic trip, right? Not too fast, but a nice scenic trip. And the train has a rate of 95 miles per hour, okay? Then it says the trip time is 10 1/2 hours. So at this point, the question is, how much time is spent on the train? Okay, well, time, rate, distance. Again, uniform rates, as we see here. We have a time, we have a distance. So this is something that requires the distance equals rate times time. So let's look at this. And this is fairly straightforward, but this gives you a little bit more practice. So the name of the young lady, I think in the problem, was actually Wendy. So I say compute time Wendy spent on the train. So again, I've just summarized what we have here. And notice I've written the 10 1/2 as 21/2. Usually, if you go ahead and convert any decimal representations into fractions, you can clear fractions and make the numbers easy. That's always a way to move forward with these problems, where you can let the logic play out and then you can kind of check your work. It's always nice as you let the logic work out and then you say, well, I think I set this problem up right because my equations are making sense. And that's always a test that you have combined the ideas correctly. So now let's look at this. So again, what do we not know, ladies and gentlemen? It's like, how much time did she spend on the train? Well, that can be our unknown. So in this particular case, we can say T, and I've got it in the box here, but I'll see T corresponds to time on train. So we can just go ahead and state that. Or you thinking, well, it seems a little bit redundant, Sorales, because you've got it right there. But, sometimes it's to say things. So now let's look at the train leg of the journey and the bus leg of the journey. And we have a time, a rate, and a distance. So time for the train is T. The rate we have is 95. And then, of course, distance equals rate times time. We get 95 times T. Now, as you notice here, the total time is 21/2. So the time on the bus will just be 21/2 minus the time on the train. So that makes a simple algebraic manifestation there. So again, just remember, if we add the two times, we should get the total time, 21/2. So you can always go back and check your algebra. And in many times, if there's an error, it's something that simple. And so it's easy to check. And then, of course, the rate is 40 miles per hour. And then, of course, if we use distance equals rate times time, we get 40 times the quantity, 21/2 minus T. So we're thinking, wow, look at that. We're good. So if you look at this, the 2 absorbs into the 40, and that gives us 20 times 21 minus a 40T. So, we start the problem without having to worry about that too. It's not going to be a problem for us. So what I've done here is you see that this just gets moved here. And why is that? Well, notice we have to find some way to solve for t. So there's got to be some part of the problem that connects the journey on the train with the bus, and that's the trip distance. Okay, so many times you will have completed the chart and you're thinking, well, where do I go next? And you go back and read in the problem, oh, I didn't use that number. And when you find the number, you know how to put the things together, the pieces together. So now if we add the distance on the train to the distance on the bus, we should get 750 as we have here. So we have what, 95t plus 20 times 20 minus 40t equals 750. Now, notice here and see what we've done here. It's not always obvious how we reduce this, but notice here, we've got a 5 in here, we've got a 5 in here, we've got a 5 in here, and we've got a 5 in here. So if you just kind of do this in baby steps, just little steps, break down the numbers. It doesn't have to be like, oh, well, I'm not sure if I've gotten the greatest common factor, but just go ahead and reduce. Of course, 95 divided by 5 will give us 19. 20 divided by 5 gives us a 4. And with the 40, we get to the 8. We got the negative here. And of course, the 5 here will give us the 15. Now, when you look at this, we can start combining numbers and maybe look for some more common factors. But notice the numbers are greatly reduced. So now we've got 19t minus 18t, which is 11t. And then, of course, we have 150 minus 4 times 21. Now, don't multiply it out because you don't need to. Notice at this point, we have a common factor of 3 here. So we factor the 3 from the 150 to give us a 50, and we factor the 3 here, and that just gives us a 4 times a 7 because 21 is 3 times 7. Okay, so looking good, the 11t we just kind of remember here. I guess I should just go ahead and write it. Didn't do much with it because I didn't need to, it just kind of hanging out. And so now, of course, we have the 28. So now notice the 28 from the 50 would just give what? 3 times the 22. Now, of course, that 11 is history because 22 is just 11 times 2. So the 11's absorb, and we're left with 3 times 2, which is 6. So t equals 6. What I'm trying to stress here is when you do calculus and when you work with trigonometry and sequences and series, it is important to be able to absorb common factors and clean up your algebra. And that really requires that you understand numbers and factorization. That's why we spend so much time on theory of equations and factorizing polynomials to get used to that strategy, because it is so essential to do the calculus. It's so essential as you do STEM mathematics to keep your work clean and efficient. So now we're like, we're done. I mean, it's like, it takes 6 hours on the train. And so notice over here, if you like, we've got bus. What about the bus time? So this is going to be what, 21 over 2. And of course, we'll just write that as 12 over 2. So that'll give us what, a 9? So we have, in this case, 2 from 11 is just 9. So we get 9 halves. So now this is just 4 1/2. So the bus requires 4 1/2 hours, and the train 6 hours, and the total is 10 1/2 hours, as it should be. So the key here is that the problem did not request the time on the bus, but it could have. Okay, so this is something you need to be aware of. Say the time that the problem had requested time on the bus, you get T and you're like, wow, I got the right answer, I'm done. Well, not quite, but it's not a big deal. I mean, if you do all of this work and you get T as 6, then you understood the problem. Okay, and so I could look at that and say, if I'm looking at your work, for a test, I say, well, that's excellent work, and I could look at that and say, I can give you pretty much all the points, maybe save 1. Okay, the idea is that if you have the logic, sometimes the toughest part of the problem is answering the question. We get lost in the idea of working the problem, and we get that nice solution and we're like, yeah, that's great. but we have to go back and say, well, did I really answer the question? And that is just a matter of being very vigilant about reading the problem. We often read a problem and then we put ideas into the problem that aren't there. And what I have to encourage you to do is read the problem carefully, write what you have down, and then put things together logically, and then let the symbols help you out using number theoretic reduction, using symbolic calculation. I mean, if you just start multiplying things out unnecessarily, you're taking your vision away from the problem. And you don't want that. You want, each time you do this, it's like, well, this is working out. I'm actually going to get a positive number. You know, you make mistakes or you get careless and t is -16, and then you're thinking, oh, what did I do? So it's better to take the time to write things down clearly and then work through the process. And like I said before, these problems aren't the main focus, but the logic that you employ is important. So you think about having done problems like this in your earlier algebra classes, and you're basically doing the same thing again, but now you're looking at it from a more mature standpoint as a college student. So take the time to work through the process and share your new ideas with your friends and help them to understand the logic. Again, I think you'll find these steps to be very useful and maybe give you a new lease on how you do these problems. So I hope this has been interesting for you. I think, like I said before, students will always request ways that can help them understand a procedure. And procedures are so important in mathematics. And once you learn it, it becomes part of your expertise. So continue to work hard, and I'll see you later. Thank you.